let's talk about this for a second. What does this mean? It's a very important question in math. What's it mean to be a solution of an equation? What's that mean? Talk about solutions. Usually we're supposed to find the solution. Usually it's the answer you're writing in the answer box. But there's more to it than that. What's it mean to be a solution of an equation? What's it gonna be? I mean, that might be involved in it, sure. Output's part of it. But what would a solution of this equation even look like, I guess? Say it again? Well, okay, the solution is related to the line. That's true. Okay, in fact, let's graph the line, and let's go from there. That might be helpful to look at the line. A lot of times in math, and we do this a lot in calculus, we do this all the time. It's helpful to think about what a graph might look like in math of an equation, for example, like right here. Okay, if you can make that connection in your mind to what this looks like and what that means, it's useful. Is the graph this equation? No, it's just one representation of the equation, right? But it's a helpful one. So let's graph this thing and see what we get. So where do we start with this one? 1. And when you say 1, well, what about the 1? Well, you see the 1 there at the end. What is that?
Starting point.
Okay, so yeah, the y-intercept, right? We see that this is in the form y equals mx plus b, right? And we see then that b equals 1, and b is the y-intercept, right? So we're going to start on the y-axis at the point, right? What are the coordinates of that point? We say y-intercept of 1.
0, 1.
Okay, if we wrote that down as an ordered pair, it'd be 0, 1. Good. Now we need to find another point. How are we going to do that? Okay, good. We see that the slope here equals 2, which is the same thing as 2 over 1 if we think of it as a fraction. The slope is rise over run, right? So we can always use that to get to a second point. So we could rise by 2, and we could run by 1, and we get to a second point right here. And what are the coordinates of that point, by the way? 1, 3. We're always going to do x first, right? So 1, 3. And then if I wanted to create the line, I'm just going to connect and extend those, right? Okay, now the graph is important here. The graph is a representation of the line. Can anybody see a solution on that line right now to the equation? Yeah, there you go. So here's an example of a solution right there. There's right? There's another one right there. How many of them are there on the line? There's 2. 2 that are graphed, but how many could we graph? In fact, how many? Infinite, right? Because every point on that line corresponds to a solution, doesn't it? Right? You can think about a line as being like a wire with infinitely small beads on the wire, and each of the beads is a point in the xy plane that represents a solution, right? So why is 1, 3 a solution? Prove to me that 1, 3, the ordered pair 1, 3, is a solution. How could I do that? Okay, but I can do it pretty easily. Here's my equation. I'll plug it in, right? If I plug it in, what do I get? If I plug that into my line, I get 3 is my y value, right? Equals 2 times my x value 1 plus 1. I get 3 equals 3, which is true, right? I could do the same thing with that point down there. If I plug that point in, I get 1 equals 2 times 0 plus 1, I get the equation 1 equals 1, which is true, right? So this tells us something really important. What does it mean to be a solution? What it means to be a solution, or what is a solution? Oops. Here's our simple definition. A solution equals values of the variables that satisfy the equation. What's it mean to satisfy the equation? Make it work. And make it true. Right? In this case, how many different kinds of variables are there in our equation? 2. So we need 2 values in our solution, don't we? Well, here they are. We need a value of x and a value of y, right? I can go about finding other solutions. In fact, we can do something kind of cool here. We could even say, let's pick an x value and find the corresponding y value that's going to create a solution. Somebody pick an x value. 3. Okay, let's pick an x value of 3. So if we're going to say, let x equal 3. So in an ordered pair, the x coordinate is 3. How can I find the y coordinate? Yeah, plug 3 into my equation and solve for y, right? The equation is what joins the x's and the y's together in a way that makes sense, right? So all we'd have to do is go up to our equation, y equals 2x plus 1. We're going to plug this value 3 in for x, and I get y equals 2 times, whoops, 2 times 3 plus 1, which is what? 7. Yeah, so we get the y value equals 7. And I guarantee if we extended this line up there, it would go through the point 3.7. That's another solution. Okay, make sense? So that's what it means to be a solution, right, to an equation. Okay, so today we're going to extend our look at lines and linear equations to systems, right? And this is stuff you've done in the past, but it's been a while. I don't know how much you did. So we're going to start from scratch here, and we're going to kind of breeze through it a little faster than maybe you did in Algebra 1, just to review this stuff. But if it's not totally, if this isn't just jumping to the forefront of your memory here, that's okay. It'll come back. So what does it mean to be a system of equations? Simple. More than one equation. Anytime we talk about a system of things in math, we're just talking about more than one of them taken together, right? That's it. Okay, so let's take a look then for a second at this system right here. System of 2 lines. Okay, let's look at each of these individually, and then we'll look at the system after we've looked at each one individually. Let's take this top line, and let's make that our blue line. Let's graph that. So how am I going to graph it? Where do I start?
-6.
-6 is my y-intercept, right? So we go down to -6, and there's a point. And now what?
Go down 5.
Go down 5 and over 3, right? My slope is -5/3. So I'm going to rise by -5. 1, 2, 3, 4. Oh, that's a little bit inconvenient, isn't it? I'm going to rise by -5, and I'm going to run by +3 to get another point. You know, what do we do in a situation like that where we're near the edge of a graph and it's not convenient to go down? What could I do?
You could go up and then go over.
Okay, I could go, instead of going down to the right, I could go up to the left. I could just do the opposite, right? Yeah, that would work. So we'll reverse those. We'll go up by 5 and left by 3. And I get points that are collinear. Those two still work, don't they? So now all I have to do is just connect and extend those points, and I've got my blue line, right? How many solutions are there on the blue line? There are 2 graphed, but in infinite number on there, right? We got 1, 2, 3 of them that we've specifically put points on, right? But there are an infinite number of them contained on the blue line, okay? There's one there, there's one there, there's one down there, right? Okay, so let's look at the red line. What about the red line? How do I graph that? Where do I start? 5. Yeah, I go up to 5, and I'm gonna make a slope triangle that does what? Very good. I'm gonna rise 1 and run 6 to get a second point. And now, once again, all I've got to do is just connect and extend, right? How many solutions are there graphed on the red line? Infinite, okay? Now let's focus on the system. Okay, it says solve the system. How many solutions do you think there are on that graph to the system? 1. Yeah, you're right. Where is it? Okay, the intersection, right? How come this is such a special point to the system? Why is that the only solution to the system? Right? Everything on the blue line is a solution to the blue equation. Everything on the red line is a solution to the red equation. What's unique about that purple intersection?
Solution of both.
It's the only place that's in both solution sets, right? It's the only place that is simultaneously a solution of the red and the blue, okay? All right, so then we could generalize this, couldn't we? We could say, really, there's only 3 things that could happen when we look at a system of 2 lines, which is mostly what we're going to do. We're looking at simple, small, linear systems, 2 lines, 2 variables, 2 lines. We can get one solution when the lines intersect at a point, and there's the point of intersection, right? What could happen for us to get no solutions? Okay, so they'd be parallel, right? The lines never meet. So that's a possibility. How could we get infinitely many solutions? And what would have to happen there? It'd be kind of a weird situation. In order for us to have, what's the only way you could get more than one intersection of lines? Same line, yeah, if they overlap, right? So if we had something like this, where the 2 lines are the same line. Okay. All right. So now let's try a couple of these. Did you notice, first of all, that graphing is not probably a great way to find solutions? I mean, what's wrong with that technique in finding a solution? What's the obvious shortcoming? What do you think, John? Okay, yeah, they may not fall at convenient places, right? And even if they do, my graph may not say that they do, right? Because there's human error. When you make a graph on paper or on a board, there's always going to be human error, right? And what if the solution really isn't at a convenient place? How am I going to know what the coordinates are, right? So graphing is a horrible way to solve systems, unless you have technology available. If you have technology, it's a great way. So everybody go to the Desmos graphing calculator. If you don't have that, that's one you're going to want to bookmark because we're going to be using it a lot. So all you got to do here is if you don't have it, just Google Desmos graphing. And that takes you here, and if you just click on Desmos graphing, there you go, and then just bookmark that. Okay? Very easy to use. You've had some experience with this already. If I just graph these 2 lines as they're written, y equals -5/3 x minus 6. Look, it gives you a nice line there. I'm going to make it blue. By hitting this little gear, you can control the colors of the lines too. So I'm going to make this blue so it matches my picture. And then down here we got the red one. So y equals 1/6 x plus 5. I'm going to make that red. So there's my 2 lines. Okay, now look at, everyone just take a glance up here for a second. I pointed this out, but Desmos is really smart. Desmos anticipates the kinds of things you're going to want to find. So if I click on the red line, look, it gives me, it highlights a little gray point here. And if I go to it it knows I might want to know that because it's a y-intercept. It knows I might want to know this point because it's a point of intersection, right? So if I click on it, the coordinates will stay there. So what is the solution to this system?
Negative 6, 4.
-6, 4, right? This is how you do math in the real world, honestly. This is, like when I was an electrical engineer, very seldom would I ever sit down, and I would sometimes, but very seldom do you sit down and just crank out a bunch of math algebraically. Now you might have to set things up with algebra, but when you want to get an answer, you use technology. You just graph it and find the solution, or use a graphing calculator or something, right? Okay, so this is this is a real skill. This is something that it's important to know how to do. Let me take a picture of this for the notes. I'm going to have you try a couple more of these. Okay, try, if you will, try this one. And I'll just work along with you. What'd you get?
Negative 5, 3.
Negative 5, 3. Okay, try that one. What'd you get there? Yeah, look, they're parallel, aren't they? So that's going to be a no solution situation, isn't it? Okay, so let's make a note of that. No solution. Yeah, one more. Try this one. Okay, what'd you get there? Infinite. Now, how do you know? How do you know that they're on the same spot? And here's one way to quickly tell. Like if you, the blue line was the first one, so that's on the bottom. This one's on top. Look, if I turn the red one on and off, look what happens. The blue line shows up underneath it, right? So you can see right away that this is definitely a case where they're the same line. Yes, sir. Yep. Okay. All right, so we had some practice with technology. Next step is, how do we do this without technology? Okay, so click those Chromebooks all the way closed, and let's take a look at one of the two methods we're going to have. We're only going to do one today. We'll do one next week. One way we can solve a system is by substitution. Okay, remember what the other one's called? Remember? Starts with an E. No. Starts with an E. E-L. Elaborate? Do you want me to elaborate on it? E-L-I? Elimination. There it is. Yeah, I knew it would happen. I knew you would. So elimination's the other one, right? As we go through these, I'd like you to think about, we haven't done elimination yet. Well, that's the one we'll cover next week. But I want you to be thinking about when you might try substitution and when you might move on to plan B, which would be elimination, okay? So substitution is really simple, and it's a useful thing to know how to do because you can use it in other situations where you don't have linear equations. Later on in the year, we're going to solve linear quadratic systems, where we've got lines and parabolas. And we want to solve those by substitution, okay? Substitution, so it works in bigger, harder kinds of systems. With linear systems, it's never really super hard to do, but sometimes it's hard enough that we want to move to plan B. The way it works, it's always the same. There's 4 steps. You got, let's say we're talking about a simple system with 2 equations, right? You're always going to identify one equation where it's easy to isolate a variable, okay? And then you're going to solve for that variable. So there's step 1. Let's just kind of go through this in order. So step 1, in this case, this is a super easy problem. We've got 2 equations where the work's already done for us. Y is already isolated in the top and the bottom equations. So we can just arbitrarily pick one. I'm going to pick the bottom one to be my substitution equation, okay? Something I want you to do, and make a note of this, because this is important. When you solve for one of the variables in step 1, always put a box around the answer that you get, because you're going to go back to that. You're going to go back to that, but later on when you have to plug in a value to find the other variable, that's where you're going to go. So it makes it easy to find if you put a box around it. So we solve one equation. In this case, we solve an equation for y. It's already done for us. Step 2, we're going to substitute. So we're going to, whatever variable we isolated in step 1, we're going to plug that into, oops, that's a horrible arrow. We're going to plug that into the other, that's not a very good arrow either. I think this pen needs to be calibrated. No, it's a little bit off. You get the idea, right? We're going to plug it into the other equation, okay? So step 2 then, what's that going to look like? Our top equation that starts off as y equals negative 7x minus 1. We're going to replace the y with whatever we have in the box. And x minus 9 equals negative 7x minus 1. Okay? Step 3 is solve. Solve for whatever the remaining variable is. Now look what happened here when we made that substitution. You might be thinking, oh, that's ugly. It looks like there's more stuff going on. But I would argue that this right here is a lot better than what we started with. How come? How many kinds of variables are there in that equation? Well, there's 2 variables that show up, but how many different types of variables are there? 1. That's what we want. If there's only a single variable in an equation, we can solve it pretty easily, right? So step 3 then is we got to solve this thing. Well, what would the steps be? You're great at this. What are the steps to isolate x here? Combine like terms. Where am I going to push the variables, left or right? To the left, good. So we'll add 7x to both sides, right? Let it show. We're going to push the numbers the other way, right? So I could add 9 to both sides. And then look what happens. The 9's cancel on the left, the x's cancel on the right, and look what we get. 8x equals 8, right? Okay, so then what's x equal to? 1. If I divide each side by 8, I get x equal 1. Am I done? No, because now I have to substitute that, right? That's why we want the box around the substitution equation. So I'm going to substitute my value of x back into the boxed equation, and what do I get if I do that? Yeah, I'm going to get y equals 1 minus 9. So what's y equal to? Negative 8. Okay, so now I've got both parts of my solution. I need an x and a y. When we want to write the solution, though, we're going to write it as an ordered pair. So what's my ordered pair going to be? There you go. And what do you think the point of intersection would be if I graph those lines? 1, negative 8. Okay? All right, let's try another one. Try one that's a little bit harder. So Here's an example, by the way, of one. I get that one crossed out. How come? Is that one that looks like it'd be easy to do with substitution? No. How come? Is there a variable there that's easy to isolate? No. No matter which one you pick, like if I just arbitrarily, maybe we'd say, well, at least that one looks the easiest. It's got the smallest coefficient. If I want to isolate that y, I'd have to subtract 4x and then divide everything by -3. I'm going to get fractions, right? I don't want to be substituting with fractions. So that's one we would not use substitution on. We'd move on to plan B and use elimination. Yeah. Okay. Do you have a question, Jeff? You sure? Got it? Okay. So that's one we would just say no to substitution on, right? This one, though, we could do. What would be an easy variable? Okay, what's an easy variable to isolate up there? Which y? Top or bottom? Bottom, yeah. And how come? Because the coefficient is 1, right? We look for variables where the coefficient is 1 or -1, and those are ones that are easy to isolate. Does it have to be a y? No, it could be x. Doesn't make any difference. It just happens to be y, right? But it easily could be x. So step 1 then, step 1 is just going to be, we're going to solve for that y. Okay, what's the only thing I have to do to solve for that y? Subtract 7x, right? So everybody agree I'm going to get y equals 22 minus 7x, or -7x plus 22, doesn't matter, right? So I got the y by itself, so I'm going to box it, okay, because I'm going to be coming back. Now what's next then? That was step 1. We isolated a variable in the bottom equation. Could have been the top, but in this case it was the bottom. What's next? What are we going to do next? Nancy, what do we do next? I isolated the y in the bottom equation. What am I going to do with that? Substitute into the top equation. Good. If I isolated a variable in the bottom, then I have to substitute in the other one. So I'm going to plug this y in right there. Okay, so I end up with, in the top equation then, I'm going to get 6x minus 5, and I'm just going to open up a quantity, empty quantity to dump it into, right? Because that's where I'm making my substitution. So 6x minus 5y equals -28, and there's what I'm plugging in for y. 22 minus 7x. Okay? Now what? Well, I've got to solve. Step 3 is I'm going to solve this thing. So what happens here? What am I going to do to solve this equation? Distribute. So we'll distribute the -5, and I'm going to get 6x minus 110 minus 5 times minus 7x would be positive 35x. And then over here I get my -28 at 110. At 110, okay. And while we're at it, what can I do with these two guys? Combine them, and that's going to give me what, 41? And then we'll go ahead and, how about if we add 110 to both sides, so those cancel. And I get 41x equals what, 82? Okay, last step. Divide by 41, and what's that going to give me? 2. Okay, I'm going to get x equals 2. Good, we're getting there. What's the last step? Plug it back in. Plug it back in. So step 4, if I plug the x back into the boxed equation, I'm going to get y equals 22 minus 7 times 2, which is 22 minus 14, which is what? What's 22 minus 14? 8. Okay, so I got my y value, I got my x value. How do I write my solution? ordered pair, 2H. Okay, that's it. Okay, one more, I'm gonna let you guys work on this. Let's try this one. Yeah. So which one, Kaylee, which one would I isolate here, do you think? Bottom, X or Y? Which one? Y, good, so the Y in the bottom, because it's got a coefficient of -1, it's easy to get by itself, right? Okay, so step one then, how are we gonna get that Y by itself? What would I do?
Substitution.
Ah, okay. What can I do to get the Y by itself? Subtract 3x, okay, so I could get negative y equals negative 3x plus 5. Now, I gotta solve for y though, not negative y, so what do I need to do? Divide by, I'd say it's easier to multiply. Look, if we do this, I'll just show you. I mean, either way, but isn't this easier to see if I just do something like that? Now I know I gotta distribute the negative everywhere, both sides, and I get, just changes all the signs. So that's gonna be positive, that's gonna be positive, that's gonna be negative, right? So I've got it solved for y, make my substitution next, right? So that's gonna go into the top equation for y. So I'm gonna get 2 times y equals 6x plus 10, and my y is being replaced by the substitution 3x minus 5. Okay, so now when we solve this thing, what do we get? Okay, I'm going to distribute and get 6x minus 10 equals 6x plus 10. That's weird. What happens now? If I try to subtract the 6x from each side, right, look what I get. I get negative 10 equals positive 10. So how do we interpret that? If the variables go away and I get a false statement? No solution, right? Okay? Got it? Okay, so for the last little bit here, why don't you try to crank out these 3 problems. The solutions are taped up on the board up there, so I'd like you just to check them as you go. If you have any questions, raise your hand. If you're not sure how you missed something, I'll make the rounds. Yes, sir.
So I've got the first part of like how to solve it without the calculator. Solve for whatever set.
Okay, so all you're gonna do is you're going to, see, here's the steps. You're gonna isolate one of the variables. So in this case, they're already done. So you could just pick, like you could arbitrarily just pick something like, we'll just put a box around the bottom, right? And then that's gonna be your substitution equation. That's what you're gonna substitute in for y. So you get 5x minus 7 equals 2x plus 14.
Okay.
Okay?